Alrighty guys, so today we are going to finish up the lesson for 1.7. This is impromptu lesson 1.7b. We only need two examples, okay? First, we're going to draw a cheesy graph. I'm only going to put a few numbers on here because they're not all that important. Let's do, I don't know, x equals positive 2, y equals negative 1, x equals negative 3. That's enough numbers. And here's what you're going to do. We're adding this to the back. Here's what you're going to do. Draw a vertical asymptote at x equals positive 2. Draw a horizontal asymptote at y equals negative 1. And we're going to put an open dot at negative 3, 0. There. This looks like the first couple homework questions. It looks like these. I think I assigned one of them. And yes? Rational functions will usually be found in diagonal zones from each other, but not always. There could be more than two, but they're not always found diagonally from one another. Okay. Now, what we're going to do is we're just going to describe all the same stuff that was on the homework, where the hole is, the domain, all of these limit notations, and the horizontal asymptotes. We're going to do the exact same thing that I asked you to do in the homework. So first things first is going to be where the hole in this graph is. The hole is the coordinates where the open dot is. So this thing has a hole at negative 3, 0. The graph simply does not exist at that x value. It also doesn't exist at this x value. So these are two different kinds of what we call discontinuities, and you don't have to know that vocabulary for now, but this is an x where our graph doesn't exist, and this is an x where our graph doesn't exist. We know, because of the previous lessons, that this occurs when we try to divide by 0. But what's happening here? Well, you learned about it in Algebra 2, but you might have forgotten. This kind of thing happens when an x of some sort, like x plus 2 or something, or 3x minus 1. Anytime an x gets canceled off the top and the bottom of a fraction, after you do all the factoring, it creates a hole in the graph. This one is a hole at negative 3, 0. Now let's tackle our in behavior. Left in behavior, so the limit as x approaches negative infinity. So take a peekaboo out here, let x get really, really, really negative. Looks to me like I'm approaching the y value of negative 1. And as it turns out, the right hand in behavior, as x approaches positive infinity, is the same number, negative 1. This, ladies and gentlemen, is how we identify horizontal asymptotes. A horizontal asymptote will be a y value that the graph approaches as x approaches one of the infinities, usually both. There. So even if you hadn't had a picture, this would have been enough for you to know that you had a horizontal asymptote at y equals negative 1, because it's what's happening at the infinities. That's the definition of a horizontal asymptote. Y approaches a number as x approaches infinities. Now let's allow our x's to approach this hole in our graph. It's happening at x equals negative 3, but you could be on the left of it, or you could be on the right of it. So let's say we're trying to get towards -3, but we're on the left side. That means we're having this kind of motion. We're doing this. Well, what y value am I approaching? Nope. As I go this way. As I get closer and closer and closer to this x value, what y value am I approaching? 0. It doesn't matter that the graph doesn't exist there. That's not important. What's important is that's where it was headed. And by the same logic, if you're on the right side of -3 but heading towards -3, you're doing this. Again, what y value are you approaching? 0. That wasn't in 1.7a's notes, but that's how it works. Because you're asking what happens as x gets closer to the number -3. You're not allowing x to go to -infinity. You're saying x, it's like you're squeezing in. As x gets closer and closer and closer to this number, what was y doing? Oh, on both sides, y was approaching this same value. Okay? We can also have this whole left-right behavior around x equals 2. Oh, I forgot to write the domain. Well, I'll go ahead and do that after we do this. So you could be on the left of x equals 2, or you could be on the right of x equals 2. Now let's see how our graph is behaving. Amberly's not here. She always gets really excited when I write with the yellow pen, so we're going to include that in the video. Approach 2, but from the left side. Okay, if you're on the left of x equals 2, you're looking right here. So now we're saying as x gets closer to this value, my y values are going towards, looks like it's pointing up to me. Is that infinity visible enough? Oof, I don't like it. Make it darker. And if we are on the right side of x equals 2, now we're over here, but we're headed towards x equals 2, that means we're doing this. Looks to me like those y values are screaming downwards. All that's left to do now, because it was part of the homework and I just forgot to do it on here, was the domain. Well, the domain is just going to be all the x values that this graph exists at, essentially hopping over the ones where it doesn't exist using unions. It doesn't exist at x equals -3, and it doesn't exist at x equals 2. So from -infinity up to -3, union. -3 to +2, union. 2 to infinity. Boom. Questions, comments, concerns on those skills? None. Okay, dokie. Yes? Oh, questions?
Was the -3 only included because it's on the x-axis?
-3,
Like in the domain?
it's not included. -3 is not included in the domain. That's why I don't have brackets on it.
Or like, is it in the domain? Like, is it used in the domain because it's y values 0?
You want to know why is it even mentioned here?
Yeah.
It's mentioned here because it doesn't exist there. So it didn't matter what this y value was. The point was the graph doesn't exist at this x value. It's simply an x I can't use, and that's why I had to hop over it with the union symbol. Just like I can't use x equals 2, I have to hop over it.
So if it was like -3, 1,
Yeah, if the whole doesn't matter where it is vertically, it's just the point is there is an x value where this graph does not exist.
For this, it's only domain.
Yeah, I'm not. It didn't ask the range on the homework. Yeah, it just didn't. It just wanted to know the domain. All right, next is going to be how do we recognize when a slant asymptote is occurring and how do we find its equation? And then that'll be it. So I'm going to write you a function, f of x equals 12x squared plus x plus 2 divided by 3x plus 1. Now, I'm going to tell you, this one has a slant asymptote. But how do I know that it has a slant asymptote? So b slash d is because. Slant asymptote because degree of numerator is 1 more than degree of denominator. So remember, this would be considered a top-heavy function. And whatever the distance between the two degrees is, that's the kind of asymptote you would have. So if this was a cubic, power of 3 minus power of 1 is power of 2, I would have a quadratic asymptote. If this was 4th degree, 4 minus 1 is 3, I'd have a cubic asymptote. Things like that. So essentially, just how far apart are the two exponents for top heavy? Since this is 1 more than this power, then the asymptote is a degree 1 asymptote, which is a line with slope. So we call it slant or oblique. That's another way of saying it. How do we find their equations? Long division. That's how. Now, that's not the same as describing the end behavior. Remember, for end behavior, what you do is you say, as x gets really, really, really big, the leading terms start to dominate the behavior. This reduces to 4x, which is a line with positive slope, so your end behavior is left, down, right, up. But this isn't an end behavior question, this is a asymptote question. In order to find this, you must do polynomial long division. For polynomial long division, your job is to try to make the leading terms match. You're trying to make this 3x turn into this 12x squared using multiplication. What would you have to multiply this 3x by to get a 12x squared? 4x. I like my like terms to line up, so I'm going to put the 4x above the x. You take the 4x and you distribute it to the divisor. So 4x times 3x gets me 12x squared. Good, they match. 4x times 1 is plus 4x. Just like regular long division, subtract straight down. 12 minus 12 is 0. That's what I needed. 1, because this is a 1x, 1 minus 4 is negative 3x. The 2 drops down like that. Again, you need the leading terms to match, and you make that happen using multiplication, not division. What do I have to multiply this 3x by to get a negative 3x? Negative 1. Distribute the negative 1. Negative 1 times 3x is negative 3x. Negative 1 times 1 is negative 1. Subtract straight down. Minus negative means plus. Negative 3x plus 3x is 0. 2 minus negative 1 gets me a remainder of 3. So if you can recall back to your Algebra 2 days, you would normally do plus 3 over the divisor. You know you're finished doing long division when down here you get something whose degree is less than the degree of the divisor. This is degree 1. This is degree 0. Since this degree is less, I'm finished dividing. But remember what we're talking about here. We're talking about a slant asymptote, an end behavior asymptote. We're talking about what happens as x goes towards positive infinity or as x goes towards negative infinity. And check this out. As x goes towards either of the two infinities, what's going to start happening to this fraction as x gets really, 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 really big? This value of this fraction becomes very small. It's going to be 3 over gigantic. And 3 over gigantic, positive number, negative number, who cares? Number over gigantic is essentially equal to 0. So because we're talking about the end here, we're talking about letting x get catastrophically large, both positive and negative. The remainder of every end behavior asymptote will always go to 0. And what's left over is your actual end behavior asymptote, in this case, a slant asymptote. So one more time, because the remainder is bottom heavy, the remainder will always go to 0. So the quotient without the remainder is the actual slant asymptote. And it's only slanted, again, because this was 1 degree more than this. If it was 2 degrees more, I'd have a quadratic here. Same trick though, remainder would go to 0 always. London?
And that also applies to horizontal.
And it applies to horizontals. So let's go back to right here. Let's go back to right here. Let's pretend we were doing the polynomial long division. What would you have to multiply this 4 by to get a 3? 3/4. So these end behavior asymptotes are always going to be found technically using long division. By the way, how many x squareds were on the top of this? 0 of them. Guess what you have to multiply this x squared by to get to this 0x squared? 0. So these end behavior asymptotes, whether they be horizontal, slanted, cubic, quartic, whatever, can all be found using long division. It's just not worth the trouble if it's bottom heavy or equivalent. It's not worth the trouble of doing the long division, but it still works. Long division always works. Okay? And that, nerdlings, is the whole lesson for 1.7b. We are officially finished with 1.7. Thank you so much.